The title of this presentation is Assessment of Third-Party Defects, such as GOUGE, DENT, or combined GOUGE and DENT. Third-party defects are coming from external interference or excavation damage. The importance of this third-party defect depends on the country. In Europe, external interference is about 50%. In US, it is only 22%. This difference is due to the urban density, which is more important in Europe. Third-party impact defects are different, like GOUGE or DENT. This is an example of combined GOUGE and DENT defect. In this slide, we make a review of the tool for assessment of third-party impact defect, and particularly the case of GOUGE. We have two kinds of tools, according to codes or according to advanced model. For codes, we refer to the British standard of the American Petroleum Institute, and in this code, GOUGE is considered as a loss of material, and the code uses the limit analysis. In a proposed model, we use a constraint modified failure assessment diagram, and in this case, GOUGE is considered as a stress concentrator, and assessment is based on notch fracture mechanics coupled with a constraint and failure assessment diagram. For assessment of DENT, the code refers to American Petroleum Institute or the EPRJ. The proposed model is based on damage mechanics. For the code, the DENT limit depth is given by an empirical value, and the ratio of the depth of the dent over the external diameter has to be less than 70%. In this slide, we look tools for assessment of combined DENT and GOUGE defect. There is also two kinds of method, codes or proposed advanced model. Codes are provided by British Gas and EPRJ. British Gas propose a formula based on Dugdale model and limit analysis. Here we propose a model and we consider that the combined DENT and GOUGE as a stress concentrator, and assessment is based on notch fracture mechanics coupled with a failure assessment diagram. To use the advanced tool for DENT and GOUGE harmfulness assessment, it is necessary to have the following prerequisite. First, failure assessment diagram. Secondly, notch fracture mechanics. Third, constraint effect and damage mechanic, and a choice for limit analysis notch fracture mechanics. What is the principle of failure assessment diagram? The fracture criterion is a function of three terms: the critical defect, the critical applied gross stress, and the fracture toughness. But it is more useful to transform this three-parameter criterion with a criterion with two parameters in order to obtain a plane representations, which is a function of non-dimensional applied stress intensity and non-dimensional load. In this slide, we present the transformation of a three-parameter fracture criterion to a two-dimensional fracture criterion. Here, the classical fracture mechanics gives a relationship between the stress, defect size, and fracture toughness, and it is transformed in a non-dimensional crack driving force versus the non-dimensional load. And the failure criterion is represented by the failure curve. Here we have a more precise representation of the failure assessment diagram. We plot the non-dimensional crack driving force versus the non-dimensional load. In this diagram, we represent the failure assessment curve of its blue line, which is spied by the following remarkable point: 0, 1, which is a point of pure brittle fracture, and 0, LR max, which represents the pure plastic collapse. This curve delimits two zones, the failure zone and the safe zone. An assessment point A is defined by its coordinate, KR star and LR star, and if this point is inside the safe zone, there is no failure. If it is on the blue line or outside, we have failure. Due to the fact that the non-dimensional crack driving force and the non-dimensional load are proportional to the same loading parameter, we can get a linear load path for the assessment point, and this loading path crosses the failure curve in point B. The safety factor is given by the ratio of the segment OB over OA. As memory, we give the failure assessment diagram element, the non-dimensional crack driving force, which is the ratio of the applied stress intensity factor divided by the fracture toughness, the non-dimensional crack driving load, which is the ratio of the applied pressure over the limit pressure, the failure assessment curve, which is given for critical situations, the assessment point, and the assessment angle. The failure curve for failure assessment diagram is given by code. For example, this formula gives the failure curve equation from the SYNTAP European code. We can note that in order to delimit the applied domain to the plastic collapse, we have a maximum non-dimensional load parameter, which is given in the SYNTAP code, but this value which depends on the yield stress of the material. We have made the assumption that the gauge is considered as a stress concentrator. In this case, we have to apply the notch fracture mechanics to assess this defect. Notch fracture mechanics is based on a local fracture criterion. We need to know the stress distribution at notch tip. In this picture, we represent the logarithm of the opening stress versus the logarithm of the distance from the notch tip. We can note that in this case, the maximum of the opening stress distribution is a little distance behind the notch tip, and we can note that there is a free part of the stress distributions, increase of the stress until the maximum after a decreasing, and which is important in notch fracture mechanics. We have in a bilogarithmic graph a linear representation of the stress distributions. We consider that the local stress fracture criteria is related to the fracture process zone, and the effective stress is the average value of the stress distribution over these stress distributions. But the difficulty is to find the effective distance. A procedure which given in the volumetric method is to consider that this effective distance is given by the relative stress gradient, which is given by this formula. And we can note in this picture how is defined the effective distance and the effective stress. We can define now the notch stress intensity factor, K subscript rho, which is the product of the effective stress multiplied by the square root of the product of pi and the effective distance. This is symmetric from the classical crack stress intensity factor. The notch fracture toughness is defined as the critical value of the notch stress intensity factor. If we represent the critical notch stress intensity factor versus the square root of the notch radius, we can see that below a critical value of the notch, the fracture toughness is constant, and behind it's increased linearly with the square root of the notch radius. This kind of graph has been seen for many materials. In this slide, we define the constraint T from the stress distribution at an ideal notch tip. According to Williams, the stress distribution at notch tip is given by this formula, in which the first time is given by the notch stress intensity factor, and its second terms is the so-called T-stress or constraint parameter. In numerical analysis, the T-stress is given by the stress difference method, which consists to make the difference between sigma y and sigma x. You can see that after the maximum of the sigma x stress distributions, the T parameter is constant. But a gauge is not an ideal notch with notch acuity equal to infinity, but it has a finite value. Therefore, the T stress distribution is not constant, and you can see in this picture, and it is necessary to define an effective T-stress. The effective T-stress is defined as the mean value of the T-stress distribution over the effective distance given by the volumetric method. It is well known that the notch fracture toughness depends on the constraint through the specimen type. This can be seen on the material failure master curve, which represents the notch fracture toughness versus the T-stress. Here, for X52 pipe steel, we have determined the fracture toughness with three kinds of specimen: Roman tie, double cantilever beam, CT specimen, and single edge notch tensile test. And you can see that the fracture toughness decreases linearly versus the T-stress. And we can consider that the fracture toughness as reference is those which correspond to the T-stress equal to 0. Therefore, in the failure assessment diagram, we have to take into account the fact that the notch fracture toughness depends on constraint. And if you consider the non-dimensional load parameter, which is the ratio of the applied pressure on the limit pressure, the basic assumption which is used in a constraint modified failure assessment diagram is the fact that the constraint is proportional to loading parameter. This picture shows the validity of the basic assumptions, and you can see that the ratio of the effective constraint divided by the yield stress is a linear decreasing function of the loading parameter. Now we see the influence of constraint on material failure master curve. First, we see that the notch fracture toughness is a linear function of the effective constraint T effective. Due to the fact that the constraint is a linear function of the non-dimensional load parameter, the fracture toughness is also a function of the loading parameter. We define the non-dimensional crack driving force as the ratio of the applied stress over the notch fracture toughness. And this gives the equation of the failure curve. Therefore, the equation of the failure curve is a function of the critical loading parameter. Remember that in the syntax code, the equation of the failure curve is given by this expression. To obtain the failure assessment diagram modified by constraint, it is necessary to put the previous failure curve equation in the graph non-dimensional crack driving force versus non-dimensional parameter. We get the following curve, and if you plot the curve for the reference fracture toughness, we get a lower curve, which is represented by the green line. The principle of damage mechanics is that failure occurs when damage D reaches a critical value. For DENT, damage is defined by the Oyon's relationship, which is given here. In this formula, C1 and C2 are material constant, and we have also to use equivalent strain and stress. One of the problems in failure analysis is to know the exact failure criterion that we have to use. Here, we will present a conventional definitions of three zones in the failure assessment diagram: the brittle zone, where we have brittle fracture, the elastoplastic fracture, and the plastic collapse. The limit of these three zones are given by, for zone 1, for 62% of the limit loading parameter. For zone 3, the loading parameter is limited to 95% of the maximum value and the maximum value. And zone 2 is situated between zone 1 and zone 3. This, the choice of the failure criterion, is of importance because in some cases we don't know if we have to use the elastoplastic fracture or the limit analysis for plastic collapse. You have to know that plastic collapse failure criterion is less conservative than elastoplastic fracture criterion. The failure zone can be immediately obtained by analysis of the domain assessment angle. And we have two limit angles, the first θ1 for the elastoplastic fracture and the second θ2 for the plastic collapse. Now we use the previous advanced tool for assessment of gouge using a simple failure assessment diagram. The following example concerns a pipe where the dimensions are given here. The diameter is 219 mm and the thickness is 6.1. It is assumed that the surface pressure is 70 bars and the material is the pipe steel X52. Here we give the mechanical property of this steel. The yield stress is 410 MPa and the elongational failure is 32%. In this pipe, we consider three defect types. The first is a central semi-elliptical defect with a depth of half of the pipe thickness. After, we consider a central semi-elliptical defect with also a depth of half of the pipe thickness. And the third is a central long branch notch. Again, the depth is half of the pipe thickness and the notch acuity is equal to 0.15 mm. Using the data and the geometry of the pipe and defect, we apply now notch fracture mechanics. For that, we make finite element computing of the opening stress distribution versus the distance to the notch tip. According to the method of the volumetric method, we can define the effective distance and the effective stress. In the failure assessment diagram, we can define the security zone and the safety zone. The security zone is a zone where the safety factor is greater than 2 and no reparation are necessary. For the safety zone, the safety factor is less than 2 and repairing the pipe defect is mandatory. Using the results of the volumetric method, we can plot the different assessment points concerning the three defects that we have described previously. And we consider this defect when they are along the longitudinal directions or in the radial directions. And you can see that the majority of defects are located in the security zone. According to the principle of the failure assessment diagram, we can define the safety factor as OC over OA, and results are reported here. You can see that for the three kind of defect, result give a safety factor greater than 2, so no reparations are necessary. Now, we determine the safety factor with the previous three types of defect by a constraint modified failure assessment diagram, which are represented in this picture. We have two curves. The first curve is for the reference fracture toughness value, and in this case, the crack driving force is the ratio of the applied notch stress intensity factor divided by the reference fracture toughness, and we have the second situation. The non-dimensional crack driving force is given as the applied notch stress intensity factor divided by the real fracture toughness, which depends on the constraint T. Here we look at the influence of a modified failure assessment diagram on the safety factor. We compare the safety factor of a classical failure assessment diagram with the safety factor obtained with a constraint modified safety factor. And you do this for the three kinds of defect: semi-spherical, semi-elliptical, and long notch. We can notice that the safety factor obtained on a constraint modified failure assessment diagram is greater than the classical safety factor obtained on failure assessment diagram, and the difference is less than 10%. For blunt defect, it is not so easy to know what kind of failure criterion we have to use. Do we use notch fracture mechanics criterion, or do we use plastic collapse? To solve these questions, it is necessary to use the domain failure assessment diagram. We have seen previously that the failure assessment diagram is divided in three zones: brittle fracture, elastic plastic fracture, and plastic collapse. Here we look again what's happened for the three kinds of defect: semi-spherical, semi-elliptical, and long blunt notch. And here we have plotted a part of the failure assessment diagram and the separation line between the elastoplastic fracture mechanics and limit analysis. And you can see that for non-corrected failure assessment diagrams, the assessment points are relevant to elastoplastic fracture mechanics, but for corrected with constraint failure assessment diagram, the assessment points are relevant from limit analysis. This is of importance because the safety factor get by limit analysis are less conservative than the safety factor get by the elastoplastic fracture mechanics. Now we look about dent assessment. To do that, we make several tests on a pipe of a diameter 89 mm and a thickness of 3.2 mm. At the end of the pipe, it is covered with cap in order to keep the service pressure. 5 tests have been made with 4 dent depths: 29% of the external diameter, 16%, 13%, and 10%. The pipe material is a A37 steel. It is a milled steel with the following mechanical property. The Young's modulus is 200,000 MPa. The Poisson's ratio is 0.3. The yield stress is 355 MPa. Ultimate strength 441, and the elongation is 30%. In the following table, we give the result of the burst test and mainly the burst pressure. And you can notice that the burst pressure is practically constant and equal to 31 MPa, however, the dent depth. Now we compare results of simulation of denting operations and experimental result. For that, we compare in the graph load versus dent depth, results of finite element simulations and experiment. And this for 3 steps. In the step 1, the pipe is dented by a rigid spherical indenter. In step 2, the load is released and we can see a spring back phenomenon. And only on step 3, the dented pipe is pressurized. For dent, a ductile fracture criterion generally used for deep drawing is proposed. This criterion was proposed by Oyon and al. And has the following shape. If you plot the damage versus the dent depth, we can see that you have an increasing of the damage and we reach a plateau. And we can define the defect limit, which is given by the depth where we reach this damage plateau. We can see for this pipe that we can get a depth limit of 7%, which is close to the code. For one test, for vessel 3, interpretation of fracture suffer of some difficulty. The fracture is outside of the dent, and as we notice on this picture. If we make a micro hardness profile near the dent depth, you can see that at the base of the dent we have a strong increase of the micro hardness value. This means that the material is strain hardening and is more resistant to the surface pressure. That explains why you have fracture outside of dent. Now we are looking to a combined gouge and dent defect assessment. For this, we use different defects. One particularity of the gouge depth is constant for all the geometry, the gouge length also, but it is only the dent depth which is different. We have 3.32 mm for the lowest value dent depth until 14 mm. In this slide, we present the result of the test for the 3 dent depth, 16% of the external diameter, 10% and 4%, and we compare the load displacement curve for test and for finite element simulations. One can note that for all the tests, failure occur at the gouge tip. In this slide, we analyze the British Gauss formula for combined DENT and GOUGE-DEFECT. We can notice that the criticalness stress versus the dent depth is constant for small dent depth and decrease rapidly and practically linearly when the dent depth increase. But this is not in relation with our test, where we can note that from 4% of the diameter and 14% of the external diameter, the criticalness stress is practically constant. This is a strong difference with the British Gauss formula. Assessment of combined gauge and dent third-party defect is made according to volumetric method. For that, we plot the opening stress distribution versus distance, and we can notice that the opening stress increase until a maximum which is beyond the gauge tip defect, decrease after, and we can apply the volumetric method to detect the effective stress at the effective distance. In this slide, I reported the effective stress and the effective distance versus the dent depth for the three kinds of tests: 4% for the dent depth, 10% and 16%. We can notice that the effective stress and the effective distance are a decreasing function of the dent depth. Result indicate that the effective stress is not constant and depends on the defect geometry. In the same time that we compute the effective stress by the volumetric method, we compute also the effective triaxiality, which is the average value of the triaxiality over the effective distance, and we can note that the product of the effective stress by the square root of the triaxiality is practically a constant.